Good day, ladies and gentlemen, and welcome to the HIS Cyberseminar conference call. My name is Jaquilla, and I will be your coordinator for today. At this time, all participants are in listen-only mode. We will conduct a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press *0, and an operator will be glad to assist you. I would now like to turn the call over to Mr. Rick Hooper, President of CUAHSI. Please proceed, sir.
Thank you, Jaquilla. Yes, welcome everybody to the current CUAHSI Cyberseminar, latest in our series. Today we're really pleased to have David Maidment from University of Texas and David Tarbotton from Utah State joining us to bring everybody up to date on what's happening with the CUAHSI Hydrologic Information System. This seminar series continues to come to you via with the courtesy of CUAHSI, and I'm sitting in for John today doing the intros. As always, we're interested in getting feedback on whether you find these seminars useful to you and what you would like to hear on them. If you have any difficulties, just use the chat box to send a note to the host. Any feedback on the seminar series, please send a note to commanager@cuahsi.org. Dave Tarbotton, our speaker today, is also helping to organize the series, so please email him any seminar ideas for next year. So let me give a brief rundown. Dave Tarbotton is Professor of Civil Environmental Engineering at Utah State University. And let's see, he has received his Doctor of Science degree in Civil Engineering at the Massachusetts Institute of Technology. He serves as coordinator of the Utah State University Water Initiative, whose purpose is to foster collaboration and interdisciplinary work across multiple colleges and departments involved in the water sciences at Utah State. David Maidment is the Engineering Foundation Professor in Civil Engineering at the University of Texas in Austin. He is got his bachelor's degree in Ag Engineering at the University of Canterbury in New Zealand, his MS and PhD degrees in Civil Engineering at UIUC, and he has been at the University of Texas for a number of years. Prior to his coming there, he worked as a research scientist at the Ministry of Works and Development in New Zealand and at EASA in Vienna. So with that, I think we will turn it over to Dave. And Dave, one quick note, we did have to reschedule due to illness. One of our seminars from this fall will be rescheduled in early 2007 from again, a third Dave Goodrich at ARS. So with this, I will turn the controls over to David Maidment to begin the seminar. There you go, David. Take it away.
Okay, thanks, Rick. I appreciate very much the opportunity to share with the group what we've been doing in our CUAHSI project, and I invited Dave Tarbotton, who's the deputy leader of our project, to present a part of the seminar also, which he will do in the middle of the presentation. David is one of the co-PIs on our project, and Ilya Soslavsky from the San Diego Supercomputer Center, Michael Piasecki, and John Goodall are the other co-PIs, Michael Piasecki at Drexel and John Goodall at Duke University. And we've got a number of others, Rick and John among them, David Valentine, Tom Widenack, Jeff Horsborough, Bora Baran, Tim Whitaker, Ernest Toe, Cedric David, and that are contributing to our project, and we want to acknowledge their invaluable contributions. So a definition of the CUAHSI Hydrologic Information System is that it is a geographically distributed network of hydrologic data sources and functions that are integrated using web services so that they function as a connected whole. And in the beginning of our research project, we were trying to figure out what is an HIS, and this is what our definition of an HIS is, and you'll see why we come to that conclusion as we go along. So in this presentation, we're going to present to you three key items. What's the current status of the project? What are the components in the first version of HIS that we're working on? And then where are we going after that, which is the digital watershed that we'd like to work towards. So firstly, what is the current status of the project? We've just completed a Phase 1 grant from NSF, which was a collaborative research project to explore perspectives in hydrologic information systems. And last February, we submitted a continuation grant for 5 years to the NSF Infrastructure and Facilities competition. And internally within NSF, that passed the review, and we're just waiting for the awarding of the contract now. That contract comes to Texas, and the PIs that I mentioned earlier are listed here who will also be working on it. There's a waters testbed network, which we'll describe in a moment, that is going to serve as the beta testers for the software. This is 10 locations in the country that are separately funded by NSF to work on different aspects of observatory development, and we anticipate that the first community-wide distribution of products from our project will occur in 12 to 18 months, depending on establishing a proper support system for answering queries for that, which we don't think our present project has the resources to do. So in our present project, we have products that we developed in the first phase, which are research-level products, and also the beginning of turning those into fully sort of battle-tested components, which we're now starting on. And if you go to the CUAHSI website, www.quasi.org.his.html, as you see here, you can probe around in the HIS site navigation and see the different components that we're working on at this moment. And we'll talk about some of those as we go through the seminar. We've got a number of partners in our project, and I wanted to highlight the fact that this is not simply a collaboration within our own team. We've got our own team with academic partners here, with our collaboration with the San Diego Supercomputer Center as a cyber infrastructure partner. We also have quite a close connection with Unidata, which is our equivalent in atmospheric sciences, with NCAR for their climate modeling stuff, the long-term ecological research, with GEON for geoinformatics, with other supercomputer centers at NCSA, the National Center for Supercomputing at Illinois, the Texas Advanced Computation Center, with government, with USGS, EPA, National Climate Data Center, and USDA, who are all building web services the CUAHSI style or contemplating doing so, and with industry, especially with ESRI, with KISTAS, which is a water resources data management company, with Microsoft, and so on. So there's a lot of effort going into building partnerships, both within our team and external to our team. The Waters Network Information System is something that NSF has asked us to set up, and this is a data system to integrate these 10 locations where waters testbed projects have been awarded. And we had a meeting 2 weeks ago here in Austin with all the PIs from this testbed projects, and we're working to build a common data system, sort of the HIS prototype with them. And that's serving as the beta test for our HIS system. So if we look at the CUAHSI community as a whole, with its more than 100 universities, our project, as you can start to see now, has lots of relationships involved in it. And so it's not just our HIS team that's supporting the whole community, it's also all our partners that we're working with in industry, government, domain sciences, and the supercomputer centers, and also internationally. We have quite a strong collaboration with the European Commission concerning a system called OpenMI that I'm going to discuss subsequently at the end of this talk, and also with CSIRO Land and Water Resources in Australia that has closely related aspirations called a Water Resources Observations Network that they're building. So let me first now move into the first of the components that we're working on, which is Water OneFlow Web Services. When we talk about water data, what we mean in this context is water data, water quantity and quality measured at gauges, sampling sites, soil water tension and water content, rainfall and snow measurements, remote sensing, meteorology, outputs from models such as weather and climate models. Of course, our main function focus is on observational water data. And if we want to get those data now, we go for climate data to the National Climate Data Center, climate data online, and we can get data about specific states and specific stations within those states. If we want to get water quality data, we can go to EPA STORAD, and we can get data for specific states and similar kind of style, but a different format here. And if you want to get data from the National Water Information System, you have another site, which is the USGS website. And each of these sites has its own output format. This is the one that comes from the NWIS data center, which gives for this particular station the Neuse River near Clayton, North Carolina, the station, the date, and the value. And USGS has committed itself to supporting CUAHSI's Get Values function, that you'll see subsequently, so that we can get these data directly out of the archive without using manual site access onto their website. In working with these different data systems, we are building observation station maps. You see maps here for the AmeriFlux towers, for the USGS National Water Information System, which has 1.6 million locations in it, for the NOAA Automated Service Observing System, which is the weather data at airports, the NOAA Climate Reference System, which is a network of very high quality climate stations. And as we work with each network, we build a station map like what you see here. And the concept is that we can then geographically federate these things so that they build an observational station map for the nation. And as we add individual investigator data, this map densifies in certain areas as we show individual data from the quasi-observatories. This particular picture, by the way, is included in NSF's request to the Congress for the budget for NSF for next year. Another reason why one would want to do this is our collaborator at Drexel University, Michael Piasecki and Bora Baran, scraped out the locations of all the data in EPA's STORET. STORET stands for Storage and Retrieval System. And some states like Florida, for example, and Arizona have also adopted STORET, Illinois, Indiana probably, Michigan, and they can very easily transfer data between their state-level systems and the federal system. But other states like Texas has not done that. They have their own water quality system, and you can see that there's almost no data from Texas in STORET, which says that despite the power of EPA, nobody's got a complete picture of the water quality data of the country. Within our state, we've been building a Texas Hydrologic Information System with support and funding separate from the CUAHSI project. And if you take those data and you just look at them on a map federated with the EPA STORET data, you can see everything works out the way that it should, and the data are just there. So a part of what we're doing is federating across different programs of the federal government and across our individual investigator sites when they're set up. But also part of it is just geographically federating data sets that are specific for particular areas and are held in different locations. And in this case, we don't care that some of the data are in Washington and others are in Texas. It's just, so far as the person doing the analysis is concerned, they can access it in common. So in doing this, we're building an observations catalog which specifies what variables are measured at each site or time interval and how many observations of each variable are available at those locations. So we've got here in Neuse River near Clayton, North Carolina, we've got the latitude and longitude of the site, we've got the discharge data that begin on this date, end on this date, and have a certain number of values. We have peak data which begin and end and have a certain number of values. We have groundwater data, we have water quality data, and we've actually teased out the values of individual data variables in this data set so that in our catalogs we know exactly what data is available and where. These catalogs are being built and maintained at the San Diego Supercomputer Center. So what we're building is a quasi-hydrologic data access system, and this is being done using ArcGIS Server 9.2, and the ESRI has contributed its resources free of charge to our project to do this. And the idea is that this will function as the map window onto the observations catalogs, and then underneath those there will be web services that enable you to get the actual data. So we're building something called HIS Server, which supports these three functions: data discovery, delivery, and publication. So data discovery says, how do I find the data I want, which means the map interface and observations catalogs, and it's a metadata-based search. Data delivery means how do I acquire the data I want, so using web services or retrieval from a local database, and that uses quasi-web services. And data publication means how do I publish my observations data, and that's our observations data model that David Tarleton and Jeff Horsborough has designed that they'll talk about in a moment. Now, the HIS service is sitting on one side of the data system, and it's implemented at the San Diego Supercomputer Center and also at academic departments and research centers. So what we're going to do during the test period with testbed organizations is implement an instance of the HIS server for each of the 10 testbed locations. And this will be identical in architecture to the national system at the San Diego Supercomputer Center. And the idea with this HIS server is that it's the core data access system. It's got to be sustainable, which means we need an industrial strength technology that's very high level of performance and high speed, and it doesn't break, and we can continuously maintain it. Then on the other side we have what we're calling HIS Analyst, which is implemented by individual hydrologic scientists using their own analysis environments. And this is extremely flexible, so it can operate on any operating system using any hydrologic model or programming language or application. And we started developing a tutorial workbook for accessing web services in this HIS Analyst. and you can look on this location here and get the tutorials that we've worked at so far, which include Excel, MATLAB, ArcGIS, Visual Basic, and Java. So the idea here is that on one side we've got a very solid, dependable, sustainable data access system, which is built using industrial strict technology. On the other side we have extremely flexible use of almost any operating system, model, programming language, or application by individual scientists. And the way that works is that the interface is mediated by web services. And at this point I'm going to turn over to David Tabberton to explain to you how that works.
Okay, so I'm going to show you how you can actually use web services to access the HIS functionality from within an analysis environment that you may be familiar with. The goal is you can do it from a system that you know and you don't have to learn a new system. This slide shows the hierarchy that's associated with the data that's available through HIS. You start from a data source, such as the USGS. Within it, they may have a network of data sets, such as a stream gauging network. Within a stream gauging network, there are sites, Neuse River, Clayton, North Carolina, and then there are variables that are measured at each site, discharge, stage, water temperature perhaps, and then there's the individual values that are recorded of each variable, for example, 206 CFS on a certain date. The web services follow this hierarchy, and these ones in red are the ones that I'm going to illustrate for you today. The Get Network Info one hasn't been developed yet, but Get Site Info allows you to specify a site identifier, and you can find out what variables are recorded there over what time period. Get variable info gets information about those variables, then Get Values actually gets the values and brings it into the system that you're working with. And I'm going to show it to you in MATLAB, because MATLAB's a really sort of powerful, fairly widely used general purpose system. In our user surveys, we found that MATLAB was used by a lot of hydrologists. So the first three lines that are shown in yellow here are essentially the MATLAB code to tell it to read the web services definition language. That's what WSDL stands for, from the website that we've established. This is at San Diego Supercomputer Center. And you don't need anything other than a computer, MATLAB, and the internet to be able to use this. You don't have to install anything. When you execute this function in MATLAB, it creates within your MATLAB system the necessary functions that you need. So the first one that you want to use is the Get Site Info, and you specify for that the MATLAB class that you're using, which I'm designated here by WS for web services, and you specify a site identifier. So you specify a USGS gauge number in this case with the prefix NWIS. And it returns back a MATLAB structure that you can drill down into, and for example, you can get the site name out of it, and we see this is the site name for, this is the Neuse River near Clayton, North Carolina. You can get the latitude and longitude attributes out of this. Now, we mentioned earlier that I guess the system is sort of supposed to be ready for general availability in about 18 months, but this you can actually use right now. It's in prototype format, so a few things may change. If you're willing to tolerate that, you can go ahead and use it. It's not closed at all. So we would encourage people to try and experiment with this and give us feedback on how it works for them. Then also within the information that's returned from the Get Site Info, one can drill down and find the variable codes associated with the information that's recorded. So I guess at each site there's a number of catalogs and a number of series of information that are recorded, and this slide shows gauge height and discharge both being recorded at the Neuse River, North Carolina, and the begin date and end date for each of those records. Then we can, if you want to learn more about the variables that are recorded, say you just have a USGS variable number and you want to find what does that actually refer to, you can use the get variable info function, and that will then return a structure that tells you the 00060 refers to discharge in cubic feet per second. With that information at hand, one can then specify the inputs for the get values function. So you have to specify the site, the begin date and end date, and the variable that you want, and you can get the information. And if you do this, what you end up getting returned back is a XML string that looks like this. For those of you familiar with XML, if not, it just looks rather ugly. But there's functions that allow you to pass that XML out into a MATLAB object, and then one can do the analysis and plot the data. So what we're seeing here is that you're getting, there's no downloading of data. You, or at least not in the usual sense of having to go to lots of websites. From within the analysis environment that you're working with, you can just run these functions, and it will go to the web service and retrieve data from the national data system. And eventually, when hydrologic observatories come online, the hydrologic observatory data would be available in the same sort of system. So this shows some of the data sources that the web services have been built to access. It's the USGS's NWIS, National Climate Data Center, STORET. There's some NASA data, Ameriflux, Unidata has some climate models, and NCAR too. So the web services that access all of these things, and what the web services do running at San Diego Supercomputer Center, they essentially extract the information from these agencies in the format that the agencies provide it. They transform it into the format of our web services, so there's then a standard format available for these application functions to use, or application systems like MATLAB, ArcGIS, Excel, and various programming languages. And the yellow lines indicate functionality that's actually operational right now. And there's no reason why it shouldn't work in Fortran and C. It's just that we haven't developed an example to demonstrate it. So this is a slide from Michael Piasecki, who's also on our team, and this sort of gives the status of what we are doing now and how web services simplify that. And I'm not quite sure, what do I do to get the animation to go? Okay.
Just click.
So right now, an analyst has to go and request information from different data sources. And if you want to integrate, for example, MODIS data, NOAA data, USGS data, there's a whole bunch of different requests, different return data you get, a whole bunch of formatting that you have to do, and it's quite a lot of work. But what the idea behind using web services is that they would essentially mediate all that function and allow a user to submit a generic request that would use the same format for getting the data from whichever data source we want to get it from. So that's the end of web services. Now I'm going to talk about the observations data model, which is a data system or database system that we've developed for essentially for hydrologic observatories to store their data. One of the things that we're doing in this project is we're really working on informatics, and we're making the point that hydrologic information science is about representing hydrologic environments precisely with data, and that's just as important as representing hydrologic processes with equations. So we're interested in the data model aspect, how to represent information with data to describe the hydrologic environment, and how one represents information can either enhance or inhibit the analysis that one can do with it. So it's important to pay attention to how data is represented just as much as we pay attention to representing process. Many of you probably actually work with data models without maybe recognizing it or acknowledging it, because a data model is simply any way that you use to organize your data. So a simple way of representing data might be in terms of what, where, and when, representing what it is you measure, when you measure it, and where you measure it. So that leads us to this notion of a data cube, which actually underlies our design for the database, representing all of these aspects. One may work with data that's continuous in space and time, and Unidata has produced these NetTDF files, the format of which essentially comprises a model for representing four-dimensional continuous space-time data, and the way it's represented allows you to perform certain analysis with it. Other people may be familiar working with watersheds, for example, Arc Hydro, which associates each sub-watershed with a point on a stream, and the area drains to a point on the line. So there's the connectivity between the terrain and the drainage network, and how that's connected again enables certain analysis. You can trace upstream and find all the area upstream of a certain point, or all the area downstream of a certain point, and things like that. So the way the data is structured enables analysis. A lot of my work historically has been with digital elevation models, and there's a number of ways that one could choose to represent the terrain. One may represent it as a grid with flow from one grid cell to only one of the adjacent neighbors. That's a sort of single flow direction model, or flow to multiple downslope neighbors. Or one may represent the terrain with contours and flow lines, or a triangulated irregular network. So that's another model for representing data. So this just is to sort of make the point that the way we represent data matters for how we're going to analyze it. So the observations data model that we've designed is for representing point observation data collected from a hydrologic observatory. We've designed it around a relational database at the single observation level. So we're trying to expose every observation to database queries so that one can sort of cross-query in many dimensions, cross-query in space, cross-query in time, cross-query across variables, and so on. It's designed to hold enough metadata for unambiguous interpretation of the data and to provide traceable heritage from raw measurements to usable information. So this is the schema that we've come up with, and it may look initially intimidating, but it's actually a fairly small schema compared to some that are available. We ask ourselves, what are the basic attributes to be associated with each observation, and how can they best be organized? And at the center of it is the table of values, and each value needs to record the variable that's recorded there. Then there's the site where the value was recorded. There's series catalogs that record values that belong in a logical sequence at a single site. There's data sources that record the organization that collected the data. There's metadata information. There's spatial reference systems associated with the sites, and so on. And then on the right is all the metadata about the actual values, the units, the group it belongs to, and things like that. There's a report online at the CUAHSI website if you want to read about this in detail. What I'm going to do now is just explain a little bit about how this works. It's independent of, but sort of coupled to geographic representation. So the hydrologic observations data model essentially is just this little part over here, where you might have a monitoring point with a site identifier and site code that could then get coupled to a representation of the geography. So we haven't tackled representing the physical connectivity specifically in this data model, rather we're coupling it to right now an existing physical representation that might be modified, and one could couple it to any physical representation or geographic representation of the watershed of interest. The way the tables work, for example, we have a table of values that lists a variable identifier. Then there's a variables table that lists things about the variable: its name, its code, its sample medium, is it regularly sampled or intermittently sampled, continuous, instantaneous, things like that, and then the units it's measured in and the category it belongs to. I've got here a sequence of slides that just give some examples, but it's much easier to explain this with examples rather than explain the schema. So this shows, if you look at the second row in the table, we'll see the variable ID is 2. If we come down then to the variables table, it says that is a discharge value. The unit ID is 2, that then refers it to being cubic feet per second. If you look at the method associated with that discharge, it points down to the methods table. It says discharge derived from water stage using a site-specific rating curve. And then there's a derived from identifier that actually points into a derived from table that then points back to a separate record in the values table that, if you look at that, it's got a variable identifier of 1, which is the gauge height. So we've got the single table here that's mixing different types of variables, and it's providing traceable heritage back, showing that the discharge value was derived from a stage value. One may have the same idea where you have a daily average discharge derived from 15-minute data. So here we've got a variable ID of 3. It says daily average. It gives the units. It says it's derived from 15-minute continuous discharge values. And now here the derived from identifier points to multiple records in the derived from table that then connect back to all of the values that specific discharge value was derived from by averaging, essentially. So again, there's provenance information there, and it's being and one can have multiple variables involved in that. One might want to group information together for whatever logical reasons. So this is an example of water chemistry from a lake where there's, I guess the variable is dissolved oxygen. There's offsets that say that it's depth below the water surface, offset value 0.2123. So these are dissolved oxygen recorded at different depths through a lake using method 4, which is a hydrolab multiprobe. And there's a group that says this is the echo reservoir profile on that date. All of these values belong to a single group, so that they can be logically recognized as belonging together. So this is intended as a database to underlie a hydrologic information system in an observatory setting. And this shows an example of what we've got going right now in the Bear River Watershed Information System, where essentially one can click on a station where there's a set of observations, and it will open up an application reading information from a database and provide analysis functionality. So a database like that across observatories will provide is what's intended to essentially support the hydrologic observatories. This slide shows essentially how all of the system is organized together and works underneath. So what we've got at the center here is the web services. We're calling them OneFlow. They access data from perhaps observatory data services that would have the database schema that I just described implemented on them. There might be data that's held centrally at San Diego Supercomputer Center for CUAHSI data that's not associated with an observatory. There's third-party data servers such as USGS and NCDC, and the web services can access data from all of them, and then they make the data available essentially two ways. One through a common browser portal that allows you to go to a map and click on points and do some preliminary data exploration and discovery, see what's available, and perform analysis. Maybe you'll be doing quite a lot of downloading. Eventually there may be a capability to upload data and actually put it in the data services via the website with proper authentication. And the protocols used are web services, web languages like HTML and extended markup language. But if you want to seriously get a lot of data and you want to work with an analysis system of your choosing, you want to really be using the web services interface to say MATLAB, as I spoke about, or GIS, or maybe S+ or Excel. Access the data through the web services, which uses the simple object access protocol and web services definition language. So essentially, this is the simplest kind of schema of how it's all supposed to work. And I guess I now hand back to David Maidment.
Okay, thanks so much then, David. So what you just saw was HIS 1.0, and we want to get that solid by the end of this academic year, in other words, by August or September of this year. And what we want to do after that is to work with and synthesize digital watersheds. And so our goal here is to ask the question, how can hydrologists integrate observed and model data from various sources into a single description of the environment? And in doing that, we're starting off with hydrologic observations data, which is what David was just showing to you, and using a relation database designed for that. Weather and climate data, we're going to focus on using NetCDF as a format, as he illustrated in the slides from Unidata. And obviously we have GIS data here also for watersheds and stream networks, and we want also later on, and this is the further down the road, to be working with remote sensing data in a smoother way. So a digital watershed is a synthesis of hydrologic observation data, geospatial data, remote sensing data, and weather and climate data into a connected database for a hydrologic region. We're doing this by building on top of a new data set being developed by, in fact it's just been finished by EPA, called NHD+. This is a portion of this for Region 17, which is in Oregon. And what they have done is they've taken the national hydrography data set at 1 to 100,000 scale, and they've delineated a catchment around every line. And so the average reach length here is 2 kilometers, the average catchment size is 3 kilometers squared, and this has been done for the whole continental United States. So this is about 1,000 times more resolved than the 8-digit hydrologic unit code areas that we're accustomed to working with up to this point. So this is an integration of national hydrography data set, national elevation data set, and also other data sets. So for example, this includes the slope, so you know the slope of each reach, the elevation of the endpoints. They've made an estimate of the mean annual flow, so you can actually draw flow maps showing the flow increasing as you go downstream, an estimate of the corresponding mean flow velocity, the drainage area for the entire upstream drainage area of every catchment, the percentage of the drainage area in different land uses, so the national land cover data set has been integrated with that, and measures of stream water and so on. So we're going to use this NHD Plus as the land base of our GIS representation in the digital watershed. This is really the land side of the water picture, and our web services are the water side. So really we're bringing together in a really effective way the land and water resource data picture here in a way that I've been working on this almost 20 years. I've never seen this being able to achieve before. We're adding to that gridded climate information. This is the DayMat, which is a daily 1 kilometer daily time step gridded version of the NCDC gauge profiles, and we've built web services into that so that you can just ping anywhere in the country and get a climate data series at the centroids of watersheds. And we've built something called Weather Downloader, which is in the HIS Analyst in the toolbook and the workbook that just automatically builds climate series at the centroids of watersheds using an IQIS application. All of what we've talked about up to this point has been concerned with data. What we found is that there's a comparable project being done by the European Commission called OpenMI, which is designed for model linking, not just data sharing. And this uses model cores as an engine that was developed in the European Commission to try to bring together simulation models from different organizations like the Danish Hydrologic Institute, Delft Hydraulics, and Hydrologic Research OneFlow. It's an open source software system at this location, www.openmi.org. Our project collaborator John Goodall at Duke University has made some experiments, and it turns out that the OpenMI also uses the data cube, the time-space variables representation that David introduced earlier, which isn't surprising because it was developed by Roger Moore at the Institute of Hydrology in Wallingford, and that's where I got the idea about 15 years ago. So again, what, when, where underlies this whole OpenMI development, which about 10 million euros are being invested in. And so what we have done, and what John has done, is he has shown that the HIS web services can be wrapped as OpenMI components. So you can take inward stream flow, daymet precipitation, you can take a piece of code and make it into a little water balance model, and you can actually run a water balance model using OpenMI, so you can actually run a simulation model, and it's calling our web services and it's calling the data, and all of that is happening in real time, pulling data from the national data sets or from a local database if you want. And you can also do this by having one model calling another. So these little modules can be models, models can call models, models can call data, models can call web services. So I think it's a very powerful concept here of integration of simulation and data. Some of the other things that we're working on is building watersheds as hydrovolumes and thinking about geovolumes as the portion of a hydrovolume that contains solid earth materials, doing better representation in volumes terms so that we're not just dealing with blue line reaches that have slope, which is what NHD Plus supplies, but we also have water surface channel, analytical models of channels. This is actually the work of one of my PhD students, Venkatesh Mirwado, who's now at Purdue, and the Iowa group is supplying a data model for ADCP current profiler data that's consistent with this channel model, and then we want to build resonance time distributions for channel elements and so on. So there's a whole set of allied things going on with three-dimensional channel representation, and also a three-dimensional surface and groundwater integration. So I've been working on for some years a groundwater data model in which we're looking to understand how we can link the surface water stuff like with NHD Plus to three-dimensional representation of groundwater systems so that we can look at surface water and groundwater integration and hydrogeologic data development. So the overall goal here is to generalize the concept of water OneFlow and say that this is a common window for water data and models that covers federal, state, local, and academic data. And the concept behind this is that the advancement of water science is critically dependent on the integration of water information. Thank you.
Thanks so much, David. It was a great talk. Perhaps a bit of information overload for those of us who haven't seen it before. I guess I just wanted to emphasize really how far we've come from where we were, 2.5 years ago, trying to figure out what, in fact, an HIS might be. So at this point, I'd like to get this open for questions. If the operator can come back in and explain, give everybody the instructions, please.
Ladies and gentlemen, if you wish to ask a question, please press star 1. If your question has been answered, or you wish to withdraw your question, press star 2. Questions will be taken in the order received. Please stand by while we compile a list.
Yes, and for those of you who would also wish to just type a chat, you can type a question in the chat box, and we can take it and ask David directly as well. Dave, I thought maybe you could speak for a little bit longer about, a little bit more about the development of the digital watershed. Do we have a sense of timing of that?
Yes, so what we're planning to do is to have the analytical, well, at least the advanced research going on this year, and then working with the testbed teams during the next academic year, in other words, from September of this year to August of next year. And the goal then is to have the digital watershed deployed at the 10 testbed sites by September of or August of 08. Now, implicit in that is the idea that we're going to have a land base for hydrology that's nationally consistent and built up NHD+, and that's something that we're likely to house at the San Diego Supercomputer Center. And so if other people want to start working on digital watersheds for different areas than the testbed sites, then essentially we'll just be able to support that from the national data set. The NHD Plus doesn't have soils information in it, but we've got the season solar infrastructure development, and that's led by Doug Miller at Penn State University, and we've got the soils data from him that I think we can integrate from that.
Okay, that's great. We have some questions coming in from Jennifer Jacobs. David, at what point, if any, will the data transfer from the host to the user? So I think the question there is the data always residing on the host, or does the user make a copy of the data?
Jennifer, what we're looking at is that the data always resides on the host, and you either use it directly, which means you're basically using the host's database like a local database on your system, or you transfer it and make a local copy in the observations database if you want to be detailed about that, or we have a simplified version called MyDB, which is a simple one-table database that you can store data in locally as you harvest it using the Hydrologic Data Access System.
Okay, and then Rick Allen also asked you the question, which we've heard so many times before. In what ways will quality control be implemented, especially for academic data? Will it be up to the data holders only?
I'm going to pass that over to David Tarleton.
Okay, I guess right now we're trying to essentially provide the mechanism for people to document as much about the data as possible. I think it's always going to be that a person has to be responsible for making sure that the data that they're using is sufficiently good quality to meet their needs. But in the database, we've got some quality control fields. Raw data goes in and it's flagged as level 0 data. Then once it's gone through a quality control check, it then gets flagged as level 1. If you have a sort of higher level product that's derived from that, it gets level 2, and so on. So we've got information for that to be recorded in the database. We're also asking for, associated with every single value, a standard deviation of the potential error of that observation to be recorded with it. So rather than just giving a number, we're saying, give me a number and tell me quantitatively what its uncertainty is. Now, we recognize that a lot of people are initially going to not know that information, so that'll be missing. But with the database there, with that capability, we're hoping that people will actually start using it, and eventually we'll get to where this information is available and part of our common practice.
Yes, let me add that maybe, David, at least in my vision would be as we have things like, a waters network or potentially the NEON network, all those sorts of data presumably have network-level QA procedures, the same way that USGS would, et cetera. So there will be, we can, through the data ODM, identify the data network from which the data comes, but there will be that heterogeneity among the networks of whatever they do, and of course the individual researchers, I guess it's always going to be caveat emptor in terms of using the data. Do we have any questions in the queue?
Yes, there's one more thing to add about that last one is we are developing tools that will allow a person to, for example, filter data and examine it and look for spikes and then decide whether to remove them. So there will be tools that go along with the database, and the first release of those is actually slated for March-ish.
Okay. And actually, there's a follow-up from Rick Allen on that, is in some ways model runs can be used as feedback information. So is there any conception right now of sort of automated QC relative to some kind of a model expectation?
Well, one of the things that I've noticed when we've been doing these water balance calculations is that you can combine precipitation from here and flow from there and evaporation from somewhere else and recharge from a fourth source, and you add them all up and pretty soon the water balance just goes off either too high or too low, and you start seeing almost immediately discrepancies in the combination of different data sources. So yeah, he's right. When you start putting things in models, you do start seeing where discrepancies are arising. And I think this is actually going to lead to a good deal more checking on the quality of the data sources that we're using than we're accustomed to doing.
Yeah, it will be a challenge, but I think it's really going to be a brave new world, seeing how that all works out.
Yes.
Let's see, let's first just do anything in the queue.
There's a lot of stuff on the chat here, right?
The chat was first with the operator. Has anybody, is anybody waiting to speak?
And your next question comes from the line of Christopher Nero. Please proceed.
I was wondering if USGS DEM data or land use data. That's my question on the...
Yeah, I see it here, Chris. In the NHD Plus, the USGS DEMs are all integrated with that. So that includes the National Elevation Data Set 30 meter and the derived products like fill DEM, flow accumulation, flow direction, slope, and also shaded relief. They've also integrated the National Land Cover Data Set. So this is NLCD, the latest version of that. So that you've got watershed and catchment scale values for all the parameters. They have not integrated the NRCS soil type data, but at Penn State University, what they've done is to integrate all the StatsGo layers across the country and then extract grids out of them. So they've got grids of like available water content, bulk density, and so on. And so what we've got here are those layers, and so we're going to work with those and work with the seasoned people to do the soil and data integration. We've also got similar data that were developed by the USGS as part of its classification, by Dave Wallach, as part of its classification of the nation's hydrologic systems to support soil and geological interpretation.
Okay, thanks. Let's try one more from the queue. If there's anybody else in the queue?
As a reminder, press star 1 to ask a question.
Okay. Then Kyle had asked a question which about how we can integrate the state HIS systems, or I guess in general the distributed HIS systems, into the national HIS system. How would that work?
Yes, so the concept there is to do like what I showed with the Texas HIS system. So in other words, we are building and hosting here at our center a Texas HIS system, and I know Kyle is doing the same for Arizona. And so the way that would work is that you would deploy to your research center or academic department the same technology, HIS server technology, that is being used at the San Diego Supercomputer Center. And because you're using the same architecture, the question of being able to integrate those is less complex, although we haven't completely figured out how to dynamically connect the distributed HIS servers at the individual sites and the national system as yet.
Right now it's just a static federation.
Yes, basically right now we have a national system at one level and we have regional systems at other levels, and we want to figure out how to connect the whole thing together so that when you go into one area, if there's more detail in a regional system, you can click on a polygon and it takes you to the Arizona system and you're in a different server, for example. But we're not completely sure the mechanics of how to do that yet.
Okay. Then Carol Johnson asked the question, will wetland spatial data such as the National Wetlands Inventory eventually be incorporated into the national HIS system?
Oh, that's a very good question, Carol. Welcome. Carol's an old buddy from years back on the GIS and environmental modeling conferences. We haven't really given a lot of thought to wetlands information. I guess the National Wetlands Inventory is the U.S. Fish and Wildlife Service that compiled that. And what we're working with is the National Hydrography Data Set, which has a water body depiction in it, but we haven't really given a lot of thought to wetlands, I have to say, Carol. But if you have suggestions about how to do that, we'd be very pleased to receive them.
I would assume that this is a static, not a dynamic inventory.
It is. It's a mapped inventory of the location and character of wetlands in the nation.
In that sense, it's fairly straightforward, but it's not, yeah. So, Carol, get us the link of the database.
Yeah. David Tabbert and I teach this stuff, and we link to that database in our GIS class, so we're familiar with that.
Okay, very good. So, are there any questions in the queue?
Not at this time.
Okay, thank you.
There's one that's from Jerry Mead. Do you have plans for incorporating biological data that is presented privately? So yes, we would like to work with biological data, and we think that's going to emerge actually out of the test bed sites. Our one in Texas, for example, we have a collaborator, Paul Montagna, and he's a benthic ecologist, and he's got lots of biological data. So we think that it's going to naturally evolve, that will go from physical to chemical and then to biological data. Now, having said that, biological data is much, much more complex than physical or even chemical data, which is itself more complex than physical data. And in the EPA work, for example, that they're doing with Direct to try to improve data interoperability with the states, they aren't even considering biological data at all. They just consider it's just too complex. So biological data we're going to sort of sidle into, and probably by working with individual aquatic ecologists and so on.
Okay, thanks. Well, we're at the top of the hour, so we probably should wrap this up. I want to thank again David Maidment and David Tarbotton for speaking today. This is the final seminar of the fall series. We will be back with you again next spring, so watch the website and watch your mailboxes for the announcement of the spring series. I also want to make sure you are aware that in, 2 weeks is the fall ATU meeting in San Francisco. There will be a quasi-reception, on the 12th of December at the Argent Hotel following the sessions at 6 o'clock till about 8 o'clock. All are welcome, and you'll have a chance then to meet David Maidment and Dave Tarbotton in a physical sense rather than in a cyber sense. So hoping to see many of you at the reception, and with that I think we will close the seminar for today. We'll be back in touch next spring, and thank you very much for everybody for attending.